spatial chirp. So in this figure, we know the reference ray follows the green path, but the path of another wavelength, say lambda, follows the blue path, blue dashed path. So at the output, they appear at different vertical positions, right? And mathematically, the vertical displacement y as a function of lambda is equal to b times sine of theta I plus theta d. Is it okay for you? So what is y? Okay, y is the displacement between the output ray and the incident ray. There is a displacement along the y direction or vertical direction. Okay, and you can see there is a right triangle here. There is a right triangle, and the b of lambda is the hypotenuse, 斜边. Displacement y should be the length of one leg, right? Which is here. And what is the length of that leg? You can use the hypotenuse, this one, times sine of this angle, right? And this angle is the same as this one, which is the summation of incidence angle theta I and the diffraction angle theta d. That's why you have this formula. Okay? And clearly, the displacement y is a function of wavelengths. Different colors will appear at different vertical positions at the output. Okay? So if you look at the output beam in this way, you will probably see something like this. Different colors spread along the vertical direction. That is the meaning of spatial chirp. Okay? And of course, this is something you do not want, right? If your laser beam has spatial chirp, you can imagine after, say, focusing at the focal point, you will see something strange. Okay. And how do we estimate the seriousness of spatial chirp? How serious it is? We can calculate the spatial spreading. Okay, what is spatial spreading? The distance between the reddest and the bluest rays. Okay, say this is the shortest wavelength. This is the longest wavelength. What is the separation? That is spatial spreading, which is denoted by delta y absolute value. Okay, and to the first order, it's about derivative times bandwidth. Delta lambda means bandwidth. This is first order approximation. Okay. Then all you have to do is to evaluate the derivative according to this formula. Okay, by some mathematical manipulation, you can arrive at this formula. This is the spatial spreading due to spatial chirp effect. Okay? And to prevent output beam from serious spatial chirp, this condition has to be satisfied. And what is the meaning? The spatial spreading due to spatial chirp has to be smaller than this number. This is the beam diameter. Okay, so you have to compare your spatial spreading with your original beam diameter. If the number is larger than your beam diameter, you can imagine spatial chirp is really serious. You will see a very obvious color tone along the vertical direction. In contrast, if your spatial spreading is much smaller than your beam diameter, your beam is roughly okay. Spatial chirp is not serious. Okay, so you have an inequality here. 不等式. Okay, and if you substitute the formula of delta y absolute value into this inequality, you can get equation 16, which we will use it later. Question?
delta y 不是说是等于是你的 special spreading 的那个就是红跟蓝的最大距离嘛？如果你的冰赛是长这样，你跟红跟蓝最大的距离是长这样，那中间不是应该就是它中间经过的就是那一段不是应该是就是很，比如说可能都是绿色的，为什么是用 delta y 小于这个 diameter 来做？
在我回答你问题之前，我可能要补充说明一下哈，这个图的意思并不是说发生 spatial chirp 之后，红光只在这里，蓝光只在这里，不是这个意思。它的意思只是说，you can imagine for each single color, you have many colors in your short pulse laser beam, right? For each single color, actually it corresponds to a Gaussian beam of finite size, not just an infinitely thin ray, right? 每一个 color 其实它都有一定的 dimension， 所以这个图其实是说 ，OK， 如果你拿一根探针在这边量它的 power spectrum， 这里是绿光最主要，但是不是没有别的颜色，还是有。你探针移到这里，你的 spectrum 会变形，蓝光变得比较重要，但不是其他的 color 没有。Okay, so I have to clarify, but I found no better way to illustrate the spatial chirp, so this is a compromise. Okay, so did I answer your question? Okay, thanks. Any other question? Okay, so just keep in mind, equation 16 comes from this criteria. Your spatial chirp cannot be too serious. Okay. Let's see one example. Actually, these parameters appeared in the previous example. G is the normal separation between the two gratings, okay, defined here. We assume it's 20 centimeters, just about this, okay? Grating pitch is 2.5 microns, so it means 400 grooves per millimeter in spec, okay? Working wavelength, the reference wavelength is 1550 nanometers, and this is the geometry of the grating pair, and the right figure shows the spatial position of the reddest component, which is 1580 nanometers. And the blue curve shows the vertical position of the bluest color, which is 1520 nanometers. Okay? But I have to emphasize the vertical axis means the relative vertical position, not absolute vertical position, because 0 means the position of reference ray, 1550 nanometers. But you know, if your incidence angle changes, your reference ray position will change as well. Okay? 所以这个位置会随着你的入射角改变，它会跟着改的。我是把它当参考，所有的 position 都以它当做参考位置哈，所以这个 1550 永远都画在0。其他是相对于它 ，OK。But what does this figure tell us? Okay. What information can you have by observing this figure? For example, if your incidence angle is 10 degrees, reddest is here, bluest is here. They are separated apart, right? But if your incidence angle increases to 80 degrees, the separation is much smaller. So which case has a more serious spatial chirp? Small angle or large angle? Small angle, right? Okay, so the simple conclusion is spatial chirp is stronger at a smaller incidence angle. Okay? So although if you observe the grating formula, the grating pair is used for stretching or compressing the pulses. It seems that theta I is a free parameter that you can arbitrarily play with. But in reality, you have to consider the spatial chirp effect. So that means theta I cannot be too small. If you push your theta I too small, you will suffer from very serious spatial chirp issue. Although maybe you cannot find there is any problem about the stretching ratio or compressing ratio. 我的重点是说，入射角本来是一个自由参数，好像你随便你玩嘛。假设你只是要拿这个 grating pair 来做脉冲压缩或脉冲展宽啊。theta I 好像你就随便玩，只要达到你的目的，你要把它展宽到多少，压缩到多少，你就自由去调。其实不是，它不是自由的，它太小会有问题，会有这个问题，这不是你其他公司看得到的。Okay, so this is also an important example. When you design a system, you have to take care of different aspects. Do not just focus on what do you want. 常常你要追求的东西会受其他的因素牵制。So you have to have deep insight about your system. Okay. This figure shows the example when the grating pair is used as a pulse stretcher. Say you have a transform limited input pulse. After passing through the grating pair, you will create a down-chirped stretched pulse, right? Why it is always down-chirped? Can you create up-chirped pulse by a grating pair? Can you? No, with this geometry we can't. But with modified geometry, maybe we can. We will see it later. 只用这样子两个 grating 平行对摆不可能你只能产生 down chirp 但是它时间上会展宽。Okay, how wide is your output pulse? Okay, remember you have seen this formula before, right? Output pulse duration is about GDD parameter. Sorry, this is not GDD. GVD parameter. D times the walking distance times the bandwidth, right? But according to our previous formula, the GVD parameter, big D, can be evaluated by this formula, P double prime, the optical path length performing second order derivative with respect to wavelengths. Okay? If you do that, you can calculate D, then you can calculate output pulse width. Okay? But where is the formula of path length? It's in equation 12 earlier. And if you want to perform second order derivative, you need to use equation 13. It's about the angular dispersion, a diffraction angle derivative with respect to wavelengths. Okay? Substituting equations 12 and 13, you can calculate output pulse duration. And I just write down the result and highlight the key parameters that you can play with. B, what is B? Here, okay? From first grating to second grating, but for the reference ray, okay? So if you increase the grating separation, you will have a larger B, so you will have a longer output pulse, okay? The first knob you can play with. Second is capital lambda. What is capital lambda? Right, grating period. So if you want to stretch your pulse more seriously, you want a smaller or larger capital lambda? smaller one, right? So that means you need a grating with larger grating density, okay? More periods per millimeter. And its impact is huge, square, right? So if you reduce your capital lambda by a factor of 2, your stretched pulse width will be increased by a factor of 4, okay? A square impact, better than B, right? The third parameter is theta d. What is theta d? Here, your diffraction angle. And if you want to stretch your pulse more seriously, how do you choose your theta d? Remember, it's within cosine square. It's in denominator, so you want it to be smaller, right? Such that you have a larger output pulse width. And how do you control your theta d to get the smaller cosine theta d?它是递增还是递减函数嘛？对不对？在第一象限它是递减函数，对不对？所以如果它要小，那西塔 d 就要大。Okay, so you can control B, capital lambda, and the theta d to determine your output pulse width. But as I mentioned, theta d depends on theta I, incidence angle, and if you consider the spatial chirp issue, the range you can play with is limited, okay? So usually we rely on capital lambda and B to control your output pulse width. Okay, so let me ask you a simple question. If I want to use the grating pair to stretch the pulse, maybe from say 10 femtosecond to 100 picosecond. So it's a factor of 10,000. And what's the problem you will encounter if you want to use this grating pair for that purpose? If you want to stretch your pulse by 10,000 times. Think about this formula. 10,000 times, that means what? Yes, you need a very large B, so you have to be rich. Your optical table has to be very large. Besides, your grating has to be very large, right? The first one doesn't matter. You only need a grating bigger than your incidence beam. That's good enough. But after angular dispersion, if your bandwidth is very large, it will spread over a large distance. And if your B is large, the spatial spreading will be very large. So you need a very huge grating as the second one. And usually that is expensive.
西塔 D 应该跟西塔 I 有关吧？
有关。
对啊，西塔 I 越大，西塔 D 应该也会越大。
西塔 I 不一定要看你的 maybe 这个，是 diffraction order， 我没有特别讨论这个。
可是如果有办法让西塔 D 降到西塔 D 变得大一点的话，你要到1000倍的话，应该没有很困难。
That's a good idea. You can try to calculate a set of parameters to see if you can achieve 10,000 stretching by controlling this one. 我想你的目的就是这两个不用太厉害，我就要靠它嘛。可以说难看行不行？你会不会遭遇到 spatial chirp 的限制？ Okay, and if we introduce equation 16 as we just deduced, the maxima output pulse width you can obtain, okay, is always limited by this number, which is determined by this formula. Okay. So the example I just showed you, stretching by 10,000 times, sometimes it's not possible because of equation 16 is an inequality. Okay? And this is finite, right? Your bin size is finite. It simply states the bigger the Gaussian bin you use, you can create a longer pulse by a grating pair. Okay, but you cannot infinitely increase your bin size. Okay， 这也是很贵的啊！把你的bin一放大，所有的东西都要放大，所有的东西价格就统统上升了。OK。Is there any way we can totally eliminate the spatial chirp? This is one simple solution, double pass configuration. Okay? Here you have spatial chirp, right? Always. But if you place a refraction mirror here, all the rays will be refracted and following the same path. So eventually it will go back to the source direction, but this time it's your output bin is here, without any spatial chirp, right? Is it okay? 你就摆一个镜子，沿原路回去的 output bin 就自动不会有 spatial chirp. And another advantage is, in this configuration, the two gratings are accessed twice, not just once. So you can double your stretching effect, okay? And without spatial chirp, right? It's too perfect, okay? But what is the price you have to pay if you use this configuration? Good, good. 哦，这个有在 lab 出没就会知道了。啊，我的 issue 就是 how do you separate your instance bin and the refracted bin, your output bin? Bin splitter? You have, if you use non-polarized bin splitter, you will suffer from power loss. Okay? If you use PBS, polarization bin splitter, you can prevent from power loss, but it's a practical issue. These gratings are usually polarization dependent. Only one polarization state will have high diffraction efficiency. The other one, the efficiency is very poor. So if you use polarization bin splitter using two orthogonally polarized states, one of them will suffer from high loss. So still not very ideal, right? But some of you have known how to solve the dilemma, right? You can use, maybe instead of just a simple flat mirror here, you can use a corner cube or periscope, 潜望镜，就是光打过来。我这个是俯视图啊，你可以这样想，打过来以后让它上去，然后才回去。那么俯视图看都是 follow 一样的 path， 但是高度不一样。Then you can separate the incidence bin from the output bin without any loss. Okay? And if you are working with fiber optics, usually you have the circulator, fiber-based circulator. 从1号 port 进，2号出，回程会从3号离开，就可以分开。It's a very convenient device. If you are working with fiber optics, you can use that. Okay, but maybe you have other solutions. I just mentioned two examples. You can use double pass configuration. Any question? Yes.
Why is the TL pulse even shorter than the original pulse?
Oh, TL pulse has to be the shortest one. It means for the same power spectrum, this one has perfect flat spectral phase. So in time domain, it's shortest. That's called transform limited pulse. So this picture might be like this. Instance pulse is chirped. the spectral phase is curved. So after the grating pair introduced another curved spectral phase but with opposite sign. So the total phase is cancelled with each other. Then output pulse is transform limited, shortest one. It's compressor. Or you can use the reverse. This is input, this is output. So short pulse in, broad pulse out. And this grating pair acts as a stretcher instead of compressor. Okay. Any other question? Oh, this is what engineers usually have to practice. 你要考虑正跟负啊，这第一眼看太完美了哦。这个又没有 spatial chirp， 又可以 double 你的这个 angular dispersion stretching ratio 啊，但是你就要面临这个问题哈。如果你要想一些方法来克服这个入射跟出射的病要怎么区分的问题。